And share screen. Then let me kick Noah out from the participants panel.
Awesome.
How do you remove somebody?
If you remove them, like they won't be able to join back in the call.
Why is that a problem?
It's not.
Your point? He said if I remove you, you won't be able to join back. It's not like he's going to pay attention anyways.
What does that mean?
No, it's not that. It's probably, I mean, he's got this dog and it's every 4 seconds, he's like, oh, we got to deal with the dogs. True story.
You like my dog, though.
I mean, your dog's fine. It's just a dog. It's a money sink that keeps you from being able to travel. That's what a dog is. All right. Oh, we did come up with a really good idea though for our custom thing for the Tesla. We're going to do a 3D print thing for the left side of the steering wheel that'll wrap around the little like roller button thing there, so you still have access to that part of it. And you fill it with sand to give you your weight, so you don't have to have your hand on the steering wheel. But we're going to advertise on Amazon as a coin holder, because what it's going to be is the very top, you slide a quarter in to lock the sand in. Holds a coin. You never know when you might need a coin for one of those parking meters or something, right? And they sell for like $150 on Amazon. These custom steering wheel weight things, or really it's like the cell phone holder that weighs 2.15 pounds exactly. Is that something you're majorly interested in? All right. So last time we looked at message queues. And for your homework, you were just supposed to bring up to date what we did the previous time. Instead of using shared memory, use message queues. So we won't spend time on that. It's kind of just a repeat of what you did before. Just got you used to using message queues. Yeah, so let's go on. Today's example is going to have shared memory in it, but we're really looking at semaphores. And we've talked about semaphores before. What are semaphores used for at the high level? What have we talked about related to semaphores?
They're like a bouncer that only allows one thing in the critical section at a time.
Okay, so we have this part of our program that we typically call the critical section. It's where important stuff is happening, and that stuff maybe needs to happen independent of any other process possibly messing with it. So we're going to be looking at that in the context, as well as the fork system call today. Have we looked at the fork system call before? I know I've mentioned it before, but okay. Well, we're going to be looking at that today. We're going to be looking at two different approaches, but semaphores come in two different flavors. So they act effectively as a bouncer that allows us, it's a special kind of integer that allows us to either decrement or increment it. And it acts as if it's in an atomic fashion. We had a question on the midterm about atomic operations. So this is an operation that occurs as if it's in a single CPU cycle. So let me get down to this. So here, I'm going to read this little spiel, and then we'll talk about if there's anything new in here. So first question that comes to mind is, why do we need semaphores? So to protect the critical common region shared among multiple processes. So if we assume we have multiple different processes, so this is typically going to be multiple things running on a computer at the same time that we don't have control over when they're getting CPU time. Okay, because that thing at that point it's out of our control. Usually we're talking about things like race conditions and stuff like that. What is a race condition? Probably would have learned that in an operating systems class. What's a race condition? What do you think a race condition likely is based on context? If we have a resource that multiple processes are all using, what would a race condition be? Yeah, when more than one process tries to access the same thing at exactly the same time, there needs to be some way of dealing with a tiebreaker. All right, so we would say that when it comes to actual system resources and things happening at the, the microsecond level or something like that, race conditions might be very difficult to referee, right? I mean, we see this in real life, and we still get people who are angry, right? You're watching a baseball game or something like that, and there's a close call at home plate, right? The umpire gets to decide whether the person was safe or not. Did the person did they beat the throw? Did the tag happen before their foot touched the plate? Whatever it is, So now we have this referee who's deciding on the output or the outcome, who got there first, whether it's true or not, right? And usually it's depending on which team you're rooting for, you see it completely different. I always find that fascinating at like parties when you're watching a sporting event. How can the color of your hat make your eyes work so differently? It's really fascinating. I mean, we're seeing it more recently with politics and stuff like it too, right? Depending on which side of an issue you're on, you really do see the details of stuff so differently. I just find that whole idea, just from a people watching perspective, just fascinating. Yeah, right. Like you're watching, like, look, he was out by I'm going to call it 7 feet. Guy hadn't even rounded third yet. Ball was already home. No, his foot was on the back. I just was doing that this weekend at the golf club, watching people get all into the NCAA basketball right now, right? Yeah, it's just, oh, you get into that? Yeah. Really? We got a couple bets. Okay, so explain to me why you watch stupid things. I myself am stupid. So by the way, this is going to be on the class. This is going to be on the final exam. Well, and meaning to the game too, you're more emotionally involved. And well, I'm not a gambler, and I can see that with professional sports. I'm a sports fan. I like watching sports, but if I'm going to watch it, I want to see it at the highest level. I mean, so what's always frustrating me about college sports, specifically college basketball is a good example. I'm an NBA fan, and I get it. I get that somebody who's a purist might say, well, the NBA no longer looks like basketball, right? It's just all played 5 feet above the rim and stuff. But I mean, you are seeing the best basketball players on the planet playing in the NBA. The guy who's riding the pine was a stud in college, right? Where you're watching like a Final Four game in NCAA, you got dudes missing layups. I don't want to watch that. You're betting on some biochem major who is about ready to fail out of school anyways, and he can't make a layup. Doesn't make any sense to me. You would really love the WNBA. Well, but WNBA just makes sense to me because now you have the best women players in the world playing in the WNBA. Every single one of them was the top player on their college team. I don't have a problem with women's professional sports versus men's professional sports. I mean, there might be maybe the levels different, the way they play the game. Probably WNBA plays more like traditional basketball. I'm a golfer, so I see the pattern in golf. The women's professional golf, LPGA, they play golf much more similarly to how like amateur men play golf. Because the professional, the PGA players, they're doing things with their bodies that God did not intend. You got these guys hitting the ball 360 yards in the air. That's not a thing. You shouldn't be able to do that. Where like the biggest women hitters can sometimes hit at 300. Normal amateur men can hit at 300, but the average women golfer hits it 240, 250 off the tee. They hit their clubs similar distances to like normal people. So that's the way golf probably was meant to be played. Where, back like Tiger Woods, they had to tiger proof all these courses because he was, on par fives, he was hitting driver sand wedge, to the green on 2 is ridiculous. Yeah, but anyways, long story short, and this is going to be on the final, this is why college basketball is stupid. So there might be a question like, why is college basketball stupid? The question is because A, Brocker likes it, and it's not real basketball, except for the best players.
But I like your version.
Yeah, that's a good one. All right. I'm going to give you a pass on that one. That was a good comeback. Okay. Let's see. So how do we get onto race condition from that? All right. So the idea of a race condition is you have more than one process going after the same resource at the same time, and there's somehow, oh, that's right, the umpire calling them out at home plate, something like that. And we have to have some sort of decision maker. Well, because things are happening so quickly at a computer, we want to avoid the reality of a race condition. So if we're thinking about this from a baseball perspective, you know, we want to try to take everything we can do to make sure that there isn't a situation where the person sliding into home and the ball are arriving there at the same time, that we don't have to have a referee to make that call. All right. So for example, multiple users are using one printer. So there's only one common critical section, you know, send document to printer to print. Say 3 users given 3 jobs at the same time. If all the jobs start parallelly, then, you know, so we have 3 different users, they're all hitting print roughly the same time. Then one user output is overlap with another. So we need to protect that using a semaphore. So something that sits between those 3 users and the printer to make sure that only one print job actually gets that single printer resource at a time. The other ones can be queued up, ready to go, next in line, whatever it is. All right. So we need to protect that with the semaphore. This effectively locks that critical section. So the idea that the printer takes however long it takes to print a page, and that's something that can only happen for one process at a time, for one of those users at a time, and not until after their page is completely done printing and the printer is returned to its idle state can the next process then grab that resource. All right. So a semaphore effectively locks a critical section. We grab the semaphore. Now we own the resource. We perform the action that we want to perform. And then once it's completely done, then we unlock the critical section, letting whoever else is competing for it grab it again. And we'll see some code examples of this shortly. So this just repeats over and over and over again. So we have 2 different kinds of semaphores. One kind is what we just described, and that would be a binary semaphore, where we effectively have a single resource. We might have a million different people all competing for that single resource, but there's one resource. Single printer, 30 people in an office all competing for that printer. And there's only 2 states. The printer's either available or it's not. All right. If it's available when you want to use it, you use the semaphore to make it yours, then you use it, and then you give it back when you're done. And while you're in that critical section, while you are printing, nobody else can use that thing. Okay. The second kind is a counting semaphore. It really doesn't necessarily do something that dissimilar, but this guy protects a bank of resources. So if we want to stick with our printer example, we could say something along the lines of, you know, let's say that you're in some kind of print center and there's 5 different printers. And let's say that, well, let's say the 5 printers are all the same type of printer. So it doesn't, when your print job gets sent, it doesn't matter which of the 5 printers it goes to, as long as it goes to one of them. Well, that means you can have up to 5 jobs printing at once. Somewhere behind that semaphore, you have to decide, well, which of those resources is currently able to take the print job on. But that first bouncer you pass is at least one resource available. All right, so that's a counting type semaphore where it's effectively a specialized integer that as resources become available, the integer counts up. So maybe you have, in our example here, you have 5 printers. So the integer is currently at 5. When somebody comes in and tries to grab that semaphore, it decrements it to 4. It's not locked or unlocked. It's protected or not protected. All right. So you might actually, for this printer example, you might actually have 2 different levels of semaphores, right? You know, you might have the level that says, can I get into the room that allows me to use one of the 5 printers? And then you might have a just in case semaphore, a binary semaphore set up that says, only let one person use this printer at once. And we can say, well, as long as you write the right kind of software on the front end that make sure that 2 print jobs don't get sent to the same printer at the same time, then we're fine. Well, maybe you're not. You could introduce another race condition there, right? You could have 2 different processes that get past the original bouncer, you know, and let's say there's 1 available, well, actually, let's say there's 2 available printers out of 5. So both of those people get in. And then the software that's in the middle tries to assign them to a available print queue. And if we don't have a semaphore on the backside to protect that print queue, it's possible that piece of software might send both of those processes to the same printer. But we want to make it that it's not possible to send them to the same printer. All right, that makes some sense. All right, so that's the idea of a counting semaphore versus a binary semaphore. Effectively, you can think of a binary semaphore as a counting semaphore that never goes greater than 1. They're effectively the same thing. Implementation under the hood, possibly a little simpler for a binary on or off, but they effectively act the same. All right. So we'll see this in code, but we have our system call for getting our semaphore. So we have our key like we've dealt with before. So this is just like we dealt with the message queue. We can get our semget. The second argument, nsem, specifies the number of semaphores. If it's a binary, then this is going to be a 1. So we only need 1 semaphore set. Otherwise, we might say, like in our example we had 5 printers, 5 resources that we're protecting behind a single bouncer. All right. So the third thing is our flags for IPC create, those kind of things we've already seen. All right, so another system call works pretty similar to what we've seen before. This is all inside of sem.h. All right, so we're going to look at a code example now that is going to, well, here, let me ask a question first. Well, I'm going to say shared memory with and without semaphores. So let's say that we have, so assume we have a shared resource. Maybe it's a printer. And we are using shared memory to manage whether this resource, just say whether this printer is available or not. So forget about semaphores, for example, for a second. All we have is shared memory, okay? And we're trying to use shared memory to decide whether something's available or not available. So the idea is that inside of shared memory, maybe we're holding an integer or something like that, and that integer gets incremented or decremented. And that tells us whether or not, if we have the baton, we're allowed to go and use that resource or something. What would we need to invent in order to accomplish this with shared memory? And we've talked about this in class a couple times. We said it out loud, but now this gives us that alternative. So we would need some kind of protocol that dictates how we use one or more places in shared memory to manage who is allowed to use the resource. All right, so let's start off by looking at an example of reading and writing using a shared resource between two programs using shared memory, only shared memory, no semaphores. All right, so let's walk through some code and let's see how this works. I'll jump over here. And let's see, we want to look at the writer with no sum. That's the reader. Writer, no sum. All right, so this guy is going to have no semaphore in it. So let's walk through this guy and see how we're implementing that. Actually, what I'm going to do before that is let's look at the reader with no sum, because we're going to use the same reader here, whether we're dealing with semaphores or not. Okay, so we have something that's writing to a resource and then something else that will read from that resource. So let's just first understand what the reader is trying to do. The way we'll run this code is the writer starts writing first, and then the reader reads from that, and there's kind of like this back and forth between the two. All right, so we have this shared memory key, very random. So just a hexadecimal value representing a key thing. So we have a struct. The struct is going to keep track of a counter. So 3 integers here. So it's a counter, whether the write is currently complete, whether the read is currently complete. So we're using, in this case, we're using a struct to keep track of, this is almost like our resource in the middle. We're using this guy to flag whether writing has occurred or reading has occurred. So we wouldn't be allowed to read from it until writing is done from it, presumably, right? That's kind of where this guy's leading. This is just the structure itself. We haven't started using it yet. But that's the idea from this. All right, and the resource we're really sharing here is this counter. Who has access to increment or decrement that counter, and then we write to the counter, we read from the counter, is what we're accomplishing in our little fake setup here. All right, so we go ahead and we create our struct. This is going to be a pointer to this guy, and I hate that syntax. Okay, so we have a couple of different things, a bunch of integers we set up and a couple of structs, things like that. When you run this, you have 2 different options, 2 different ways to run this. You can either give it no command line arguments, and then it just assumes that the total count for this is going to be 10,000. Otherwise, you can provide it with a total count greater than 10,000 if you want to. Just from a C perspective, this A to I thing, anybody know what that does? This function right here, A to I. What does that look like it does? Should be fairly self-explanatory by looking at the code. Should be able to read code even though you haven't seen it before. What kind of value is total count?
Does it do a conversion from like the argument to an integer? Is that what it is?
Well, what kind of value is argument? Char pointer, which is effectively a what? Well, a char pointer, that variable holds an address, but what kind of value what kind of value are we trying to represent using a char pointer?
String.
Great. Yep. So A to I converts a string to an integer. Integer.parseInt. This is same thing as Java's integer.parseInt. All right. So if we take it a command line argument, why is it bucket 1 instead of bucket 0 for that command line argument? What's bucket 0 in C style command line arguments? Up here, we have 2 different things, right? We have the argument count, and then we actually have the arguments that were passed in. The argument count is the number of arguments. This guy is the collection of strings that were passed in. Why are we getting, if I called this guy and I passed it 25,000 as my command line argument, why does that live at bucket 1 instead of bucket 0? What lives at bucket 0 in C programs? And I'll tell you, if we wrote this in Java, the command line argument we're looking for here would live at bucket 0. It's a difference between the 2 languages. think we looked at this first week of class, maybe just as like an example when we're looking at hello world with command line arguments or something like that. Anybody know what bucket 0 is always for command line arguments in C, which then implies arg C is always at least a 1. If you pass it no command line arguments, arg C is at least is still 1. So what do you think that one thing that gets passed in is? Got nothing? No guess? It's the name of the program. Name of the program will get passed in. So if in this case we're running writer nosem, that's the name of the program I'm running. That's the first parameter. The bucket 0 will be the name of the instruction, the name of the program that you're running. Okay, it's I would say from a Unix perspective, an important distinction between C-based languages, well, between C and more modern C-based languages. Most more modern languages, because they don't necessarily rely on command line arguments solely, don't actually take in the name of the program. So just kind of an interesting thing. So if you were to pass a actual command line argument here, it actually lives at bucket 1. All right, well, this if-else structure, just its whole goal is just for setting this variable total count. Total count either defaults to 10,000, or if you wanted to put in something different that was greater than 10,000, it'll let you do that. Otherwise, it's going to set it equal to 10,000. You can't set it to 4,000 or something for no good reason. Just that's the rules that this conditional has set up. All right, so we can just make the assumption here that we're going to call this with no command line arguments. So this variable total count will be equal to 10,000. Fine. All right, so now we're at our normal shared memory get thing, just like we've seen before. All right, so we're going to get the ID for our shared memory. And now it's not attached to a memory location yet. We just have this unique identifier. We've reserved a place in memory that is allowed to be shared among more than one process. All right, this says, did something go south? If it did, exit. We're still kicking, we're good. Now this is where we actually attach to that shared memory. All right, so our shared memory ID, that's what was returned by shared memory get. And we're attaching this and storing that pointer. This is going to be a memory address, the memory address inside of shared memory. And we are attaching it to this variable, shmp, which is our pointer to our shared memory segment, which was this guy right here. So we have a pointer to that particular struct that's holding those 3 different pieces of information. All right, so the idea here from our program's perspective, we have a place in shared memory that's holding a struct, and that struct is going to have 3 integers in it that we're trying to kind of pretend are semaphores-ish. All right, because remember, our goal here is we're trying to look at this code from the perspective of what if I don't have semaphores, or I don't know about them, or whatever it is. I'm trying to fake it without semaphores. All right, so we got this struct. So we'll go ahead and attach. So we've just gotten some generic memory here when I'm associating it with our structure. And notice the size of the memory we asked for from our shared memory get was enough memory to hold one of those structs. That's what we asked for. Said, give me a plot of land in shared memory space that's big enough to hold one of these structs, because that's what I'm going to put there. So I'm going to have a couple different programs using that same place in shared memory. All right, and again, remember this is the reader here. So presumably the writer is going to be writing to this place. The reader is going to be reading from this place. All right. So now, assuming we're still kicking here, we've successfully attached to our place in shared memory. That we presume there's at least one other process, in this case, probably our writer, that's also attached to that, and he's doing something there, right? All right, so if we're still kicking, our goal here as the reader program is we want to read from that shared memory location. We want to read our shared resource. In this case, our shared resource is the counter. All right, so what are we doing here? We're gonna keep, this is we usually would call this a busy wait loop. So we're gonna keep spinning as long as write complete has not been is not set to a 1. The default value for it presumably is a 0. So if it's currently a 0, if write complete is a 0, that means our writer program hasn't finished writing. Is it a 1? 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 Over and over and over and over again until that guy finally sets it to a 1. So as of right now, we're going to sit here and we're just going to keep spinning as long as write complete is not a 1. So this basically says, as long as the other guy hasn't finished writing, keep checking. And what am I doing here? I'm waiting. I think this is 0.003 of a second. I think that's what sleep 3 means. I think it takes in a number of milliseconds. Well, is it seconds? Well, it says it's seconds. So I guess it's going to wait for 3 seconds. So it's going to say, was it done writing? If not, go to sleep for 3 seconds, check again. Check again, check again. So this guy's going to keep spinning here and waiting 3 seconds until finally this place in shared memory has listed it as writing is complete. Then I can fall past it and I can say, I'm going to read from that shared memory place. And the thing that I'm reading from is the counter, that resource that was being written to, that's presumably now done being written to. Why do I know it's done being written to? Because write complete is finally equal to a 1. That makes sense? But my mechanism for doing that was this while loop with this waiting thing inside of here, where I just arbitrarily picked an amount of time that says, how often do I want to check? That's what that says, right? All right, so then we'll finally read from it and show what the counter is. And then we're saying that we're done reading. So we'll mark read complete as 1 because I don't know, we're a good Samaritan or something. So now we've effectively finished the struct, right? So read complete as 1. So now we should have write complete as 1, read complete as 1, and count as whatever count ended up going up to. That was our shared resource, was this counter variable. All right, so then we'll go ahead and detach from our shared memory and then print out, we're done writing or done reading. All right, so this is how shared memory will work. This is how let's call it a fake semaphore might work for shared memory. Now, let's go to our writer no sem. All right, we still have our same key. Now, presumably this guy is his job is going to be to change the counter. And then ultimately, as soon as he's done changing the counter, set write complete to 1. If he's married up to the protocol that we have on the other side. All right, because our protocol is kind of relying on this struct that has 3 integers in it. Count is the thing that I'm sharing. Write complete lets me know when one guy's done, and read complete, in case anybody cares, lets you know when the other guy has finished. All right, so we have this function called shared memory counter increment. All right, and he's going to take in a process ID, a pointer to that structure, and then this total count variable, we'll see in a second. All right, so we have all of our variables defined up here. Total count defaults to 10,000. We've already had the discussion whether it's 10,000 or something else if you passed in a command line argument. We'll go ahead and spit out that the total count that we're attempting to achieve, we're trying to increment count by some number of things, is going to be whatever was read in for total count, or the default value of 10,000. We'll go ahead and get our shared memory. Again, it's the perfect size for a shared memory segment struct that we defined up top. That's just a struct that holds those 3 integers. As long as everything went okay, we're still here. We'll go ahead and attach it to our local struct. So now we're dealing with shared memory through that struct. All right. will initialize the counter to 0. I probably would have initialized both the reader or both. I would probably would have initialized the write complete to 0 as well, instead of relying on the default value being 0. Because we kind of know the other guy's waiting for it to become a 1. So presumably it didn't start off as a 1, right? So I maybe would have done that, but that's fine. All right, so here's our fork system call. Let's go back over here. We might already have a slide for this. Let's talk about it again. Fork system call. This guy creates a duplicate process to the current running process. Fork returns effectively an int. It returns a process ID. PID. If it returns a 0, you are the child. If it returns a non-0, you are the parent. And what it returned is the PID of your new child. All right, so the fork system call clones a process. So you're running along and all of a sudden a process literally clones itself. As soon as we hit that fork system call here, when we get to line 60, 2 versions of this program are now running. Simple as that. And both of them continue running at line 60. They don't start over. They hit line 60 and there's literally 2 of them now. Now they have to ask the question, who am I? Am I the original or am I the clone? Well, if my process ID is greater than 0, that means that I am the parent. And I just created a child and the process ID of that child is stored inside of PID. In this particular case, we don't necessarily care what that process ID is. We just happen to know that we are not the child. Because effectively here with fork, since we just split ourselves into 2 separate identical processes, presumably we have 2 different tasks that we want to complete. We might have one task that we do for the parent. We might have a different task that we do for the child. So if we're the parent, what are we going to do? We're going to call our function, passing it the process ID of our child in this case, our address of our struct, and then our total count. If we're the child, we'll call that same function, again, passing in the process ID, which will be 0 in this case, and the same stuff. But then we also kill ourselves afterwards. That's what the child does. The child calls this counter increment, but then dies, does not continue on down here. So the child process will never get down to this while loop. Only the parent will get down there because return makes a function. In this case, my function I'm currently in is main, makes it immediately end. All right, so let's go take a look at the shared memory counter increment function down here. So this guy takes in a process ID, a pointer to our struct, and the total count. It's going to set up some variables here. We'll go ahead and get a local variable called counter and set that equal to the struct's current counter. Oh, yeah, so it did do it. So then I'm going to go ahead and 0 out write complete. This writing is not complete. This guy's job here is to write to shared memory. So he's going to say, I have not written to shared memory yet. So I'm going to say, I'm grabbing this resource. All right. So then we're going to say, well, if I was the child, I'm going to go ahead and advertise that, oh, I'm the child and I'm writing. If I was the parent, I'm going to go ahead and just advertise that I'm the parent and now I'm writing. So we would see 2 different processes running. When we run this program one time, we will get two separate processes, the original parent and then a child who also goes and does some writing. Make sense? So we have two different processes trying to write to that same place in shared memory. All right, now, and keep in mind that both of these guys wrote the write complete equals 0. So we're going to increment that counter in shared memory by total count in steps of 1. So we're just going to keep incrementing it, add 1 to it, then add 1 to it, then add 1 to it, then add 1 to it, over and over and over and over again. All right, so num time starts off at 0. Num time is just a variable, modern day C, we could have said for int I equals 0, I is less than total count, I plus plus. But historic C would not have actually allowed you to define that here. So that's why they have it defined prior to this guy. All right, so this loop just goes through total count number of times. We're going to do something by our default value 10,000 times. What are we going to do? Well, we're going to increment a variable, and then we're going to set that location in shared memory's counter variable equal to that new number. All right, so it'll go from a 0 to a 1 to a 2 to a 3 to a 4, so on and so forth. All right. Then we're going to tell it to go to sleep for some percentage of time. So sleep time is going to be 1,000th of the number of the current count, it looks like. Oh, sleeping for 1 second for every 1,000 times through. That's what this modulus, that is what the math does. All right, so sleep for a second every 1,000 times through there. So if we have 10,000, we're going to sleep for 10 seconds total, but only each 1,000 times will we actually take a break. Otherwise, we're going to keep zipping through this for loop. So the for loop will go through freewheeling 1,000 times, then go to sleep for a second, freewheel for 1,000 more times, go to sleep for a second. Okay, now keep in mind, this is a different process, right? So there could be another process, a duplicate process, whether this is the parent or the child. We have another process that's sleeping, but presumably they might be a little bit off, right? They're not necessarily synchronized, okay? But they're both sharing the same place of shared memory. So the single resource there in the center, and we have a parent and a child both trying to increment values inside there. All right. Once this is complete, once we've done the total count number of times, now notice here, I just want to point out, counter is a local variable. All right, it's a local variable that was defined as part of the shared memory counter increment function. So it is counter that we're incrementing here. And then we're setting that shared memory counter equal to whatever that counter was. Okay, we're not incrementing shared memory counter in place. We're incrementing another variable, and then we're overwriting this place in shared memory with that variable. Okay. Now, soon as this guy is done, whether it's the parent or it's the child, it says, I'm done. He's going to mark that thing off as he's completed his task. Okay, again, presumably the parent and child might not finish writing at the exact same period of time. All right, but they're still fighting with that same place in shared memory. Okay, so somebody is going to set this guy to 1. We don't know who's going to set it to 1 first. Could be the parent, could be the child, right? But whenever this guy gets set to number 1, now that reader can start reading from it, right? That's now allowed. The reader can read from it. So then we just ask the question, if I was the parent, I'm sorry, if I was the child, meaning my process ID was 0, I'll just spit out child is done writing. If I'm the parent, I'll spit out parent is done writing, whatever. That's what this function does. It just increments that place in shared memory. But we have two separate processes that are running simultaneously, both incrementing that same value in shared memory, both changing whether I'm done writing at the same time in shared memory. Okay, so these guys are competing with for that same resource. And what have we done up here? So when we first create the duplicate, we tell the parent to do their right thing, and we tell the child to do their right thing. But as soon as the child's done, we kill it off. All right. So when we get down to this while loop, the only person who's participating in this while loop is the parent. Does that make sense? So what's the parent doing here? The parent is saying, I'm going to take a nap for 1 second over and over again until the child has completed. Now, the child may have already completed the first time we got to this while loop. We don't know who finished first between the parent and the child, right? We're at the mercy of process scheduling or whatever it is. But that's what this says. Parent, wait till this guy, I'm sorry, not the child's finished, but wait for the reading to complete. Sorry, what I just said actually before is incorrect. This guy's not waiting for his child. He's waiting for the reading process to finish reading. So he's going to sit here and wait for, he's presumably already finished writing to this place. And now he's waiting for that process that's reading from it to say, I've read the count. Now I've marked it as 1. I'm done reading. Boom, you're done. Then he's going to go ahead and detach. And then he'll be able to write out writing process complete. So let me just run this real quick so we can see how this is working. So I'll come over here. And I'm going to write, we're going to call writer no sem first. All right. So the parent and child are both now writing. Presumably they both finished writing now, correct? Okay, they both finished writing. Okay. Well, now they're finished writing. Okay, now they finished writing. But that parent is still sitting there waiting. He's waiting for the reader to finish reading. So we'll come over here to the reader. So we got a shared memory counter of 1,000, detach from shared memory complete. This guy now finished because we finally read from it. He was waiting for it to finish reading from it. If I go back into reader real quick, we want to look at what is he writing out for that shared memory counter that is 11,000. Why is it 11,000 and not 10,000? There was 2 processes competing with that guy, right? Would it be on time? All right, so homework. And I'll push this code up. Why, when not using a semaphore, does the reader think the total count is 11,000 instead of 10,000? Make sense? So go through, we just went through every line of that code. Tell me why the reader is getting a different count. Really what you want to look for is, tell me why the writer is counting extra with that parent-child situation. Go ahead.
Will it always be 11,000 or will it?
I think in this case, it's always going to be 11,000. I can prove it here real quick. Yeah. So you tell me why. It'll always be 11,000. Just so I don't forget here, I'll go ahead and push this to GitHub. And I will see everybody on Wednesday.